Okay, all right. Well, happy Monday to you all. How do I full screen? Okay. All right. We'll take a look at today's lecture. I've titled Bayesian Basics. It's really just about the beta distribution. Well, I guess some basics on some Bayesian concepts as well. So the class is titled Monte Carlo Methods, but I would say our primary application is for Monte Carlo methods is often in Bayesian statistics. So I wanted to try to motivate the use of Monte Carlo methods by kind of covering Bayesian stuff first, and then giving you kind of the context for that, and then you can maybe understand why we would bother using Monte Carlo methods and things like that. Okay, so before we get into Bayesian stats, I think it's useful to compare it to kind of frequentist ideas, and so we'll review some things from frequentist statistics. These are often seen as kind of opposing views regarding probability. And in frequentist statistics, probability is defined as the long-run relative frequency of an event. And so long run means, approaching infinity. And so when a frequentist says something like the probability that a coin lands heads is 0.5, that means that after an infinite number of flips, the proportion of times that the coin lands heads is going to be 50% or 0.5. Okay, and obviously, we can't achieve infinite coin flips in our reality or our lifetime, and we might achieve like 1 million, okay, or 100,000 or 1,000 or whatever. But we're just saying we're expecting if you do a whole bunch of these flips, it's going to be something around 0.5. Okay, and you have things like maximum likelihood estimation and confidence intervals, and these are both ideas that kind of stem from this frequentist statistics viewpoint. A lot of times in frequentist statistics, if you have some kind of unknown parameter, it is treated as a fixed value, but it's unknown, okay? So, when we do something like maximum likelihood estimation, we have a probabilistic model, and we say this is what we believe the system to be that generates our data. So we're looking at our data, and we're saying our data is coming from some kind of thing that has random properties, and this is how we're observing the numbers that we have, okay? And that model, that probability model that is generating our data, is going to be defined by parameters, okay? And in frequentist statistics, these parameters are fixed values. They are somewhere in there, they're set in stone, okay, by the universe, but they are unknown to us, and we're trying to figure it out, okay? So, for example, I have this bag here, and let's say this bag is full of marbles. It's full of batteries, actually, but and we're going to say in this bag, some of the marbles are blue, and the rest are not blue. Okay, and we want to estimate what proportion of the marbles in this bag are blue. Okay, and then so there's some proportion in here that is unknown to you. Okay, but this is our model for generating our data, because what we're going to do is we're going to draw marbles out of here. We're going to draw, say, like 10 marbles with replacement, okay, and then we'll look at kind of the colors of the marbles that we get, and so the probabilistic model that we would use to explain the generation of our data would be a binomial model. Right? We would say, there's in this bag we have basically two colors, blue and not blue. Okay, so I mean maybe it's blue and red, or it could be blue and any other colors. but we're just really focused on whether it's blue or not, so we can kind of dichotomize our thing. And then because we're drawing with replacement, we're going to assume that the probability of drawing a blue is going to remain constant throughout the whole thing. And so how do we explain the data? We would use a binomial model. And therefore, when I draw 10, I get some, let's say I get 6 blue marbles. If you were to draw 10, maybe you would get a slightly different number, okay? And if we all did it a whole bunch of times, we would expect, the distribution of our values to follow that of a binomial distribution, okay? And the idea here is that there is some proportion in here, some theta, that is unknown to us, okay? But we want to estimate that. Now, at any given time, I could, in the frequentist view, I could just kind of open up the bag, dump everything out, okay? Count up how many marbles I have, and I could get the exact proportion that's blue, right? So there's some, that the proportion of blue that's in this bag is not some random thing, it's a fixed value, okay? And that's the frequentist approach. And so when we do something like this, we would use maximum likelihood estimation, and we'd say, okay, if you have 10 marbles, or if you drew 10 marbles with replacement and 6 of them are blue, what's going to be your maximum likelihood estimate, okay? And I think intuitively we can kind of guess that it's going to be 60%, but we'll work through the math, okay? So we drew 10 marbles with replacement, 6 are blue and the rest are not. We're going to find the maximum likelihood estimate for theta. And so we will begin by using with a likelihood function of the data that we observe, okay? And so we want to find the value of theta that's going to maximize this likelihood. And so our likelihood function, okay, is basically our binomial probability, 10 choose 6, theta to the 6, that's going to be the probability of getting a blue marble, and that happens 6 times, so it's going to be theta raised to the 6th power. The probability of getting something that's not blue, 1 minus theta, and we're going to raise it to the 4th power. And basically our maximum likelihood estimate, our theta hat that we're going to get, is going to be the value of theta that maximizes this quantity. Okay, so it's argmax theta of basically our likelihood function, where our data is 6 blue marbles, okay? And so the way we're going to find the maximum here is we're going to take the derivative with respect to theta, we'll set it equal to 0, we'll find where theta has a derivative equal to 0, that's going to correspond to critical points, we solve for that, and we go, right? So, when you're dealing, over here we've got kind of a big product. This is the result of our sequence of independent events. Every time we draw a blue marble, that probability is theta, and that happens 6 times. Every time we draw something that's not blue, that probability is 1 minus theta, and that happened 4 times. So that's why we have theta to the 6 and 1 minus theta to the 4. And we're going to take, in order to kind of make our lives easier, we're going to take the derivative, take the log of it, which turns the product into a sum. So 10 choose 6 is 210, so that's where this log 210 is coming from. And then theta to the 6, the log of that becomes 6 log theta. 1 minus theta to the 4 becomes 4 log 1 minus theta. Now we take the derivative of this with respect to theta, okay? These things, log 210 zeros out, 6 log theta becomes 6 over theta, and 4 log 1 minus theta becomes 4 over 1 minus theta, and then you apply the chain rule for the minus theta to negative 1 there. And then we set that equal to 0, and we're going to solve for theta. So setting that equal to 0, I bring this over to the other side and multiply both sides by theta times 1 minus theta. I get 4 theta is equal to 6 minus 6 theta, and I get 10 theta is equal to 6, or theta is equal to 0.6. So our maximum likelihood estimate is 0.6, which aligns with kind of our intuition that if I were to draw 10 marbles out of the bag and 6 of them were blue, what is your estimate for what's in the bag? You would say, yeah, based on our data, I'm thinking my bag is 60% blue. And then, if that were the case, okay, so according to frequentist statistics, the best estimate for the proportion of blue marbles is 0.6. and we observe, because we observed 10 and 6 of them were blue, you would also probably have to estimate a standard error and say, yeah, you know what, how reliable or how much error is there around this estimate of 0.6? And there's probably a decent amount of error because we've only had 10 observations, okay? And then if I say, hey, I want you to make an estimate or use that value to make kind of future guesses of probability. And then I could say, hey, what's the probability that if I draw 3 more marbles, what's the probability I get 2 blue marbles, right? And then so now you just kind of plug in your guess of 0.6 into a binomial probability. You do 3 choose 2, 0.6 squared, 1 minus 0.6 to the 1, and you get 0.432. And so that's kind of how maximum likelihood estimation goes. I think you guys did this in 100B, is that right? And you probably did it for a whole bunch of different probability distributions, but the binomial one is, one of the easier of the maximum likelihood estimation things, but it serves as a good thing here. So, okay, so that's kind of the frequentist approach for maximum likelihood estimation. You're saying this is going to be the value of theta that maximizes the likelihood of the data that I observed. Okay, so we could create a confidence interval. I'm just making up numbers, okay? So I'm going to pretend that if we made a 95% confidence interval, my margin of error is 9 percentage points, okay? And if that's the case, if 60% is my estimate, then my 95% confidence interval would go from 51% to 69%, okay? Or 0.51 to 0.69. And then I think, I don't know, when you guys learned confidence intervals, did your professor or your teacher make a point to say that you have to use the word confident and you can't use the word probability? So your interpretation is something like, I am 95% confident that the proportion of blue marbles is between 51% and 69%, okay? And you are not allowed to say there's a 95% probability that the proportion is between 51% and 69%, okay? And the reason for that is because that proportion of blue marbles in this bag is a fixed value. It is not subject to randomness. So in frequentist statistics, the word probability only applies to kind of random events. So before you flip a coin, you could say, what is the probability that the coin will land heads? And you would say 50%. Okay? However, once somebody flips a coin and it lands, it is, in frequentist statistics, it is a nonsense question to ask what is the probability the coin has landed heads, because it either did land heads or it didn't land heads, so there's no more probability there, okay? And because you don't know how it landed, you have to say I'm 50% confident that it landed heads. That's the frequentist approach, okay? And the same thing here is that there's no probability going on here. Inside this bag, there's marbles that are blue and marbles that aren't blue. And if I wanted to, I could open up the bag, I could count up all of the marbles, and I would know exactly what proportion are blue, okay? And there's no probability there, it's a fixed value. And so we are not allowed to say, there's this probability that it's blue. It's either blue, it's either between 51 and 69%, or it's not. We don't know what it is, so we say something like, I am 95% confident that it's between these two numbers, but that's what we have there. Okay. So that's kind of the frequentist approach. In contrast, in Bayesian statistics, this unknown parameter is not a fixed value, okay? We treat the unknown parameter as a random variable. So I would say in certain contexts, Bayesian statistics, like in this approach with a bag and if I am able to kind of unzip the bag and dump everything out, then I would say a Bayesian approach doesn't quite make sense, okay? Because it feels very much like, oh, I could just check and there is a set number. There's we wouldn't say that there's forces of randomness here, okay? And so, yeah, I think I wrote that. I said, treating the unknown parameter as a random variable might not make sense if the example is a box or a bag with marbles in it, because at any time we can kind of open up the box, dump out the marbles, count them up, and find the exact proportion, okay? But I would say there's a lot of other things in life where it does make sense to treat the unknown parameter as a random variable because it is subject to random changes. So for example, I could ask, what proportion of people in the United States are under the age of 18? Okay, so this is kind of like a measure of how young your population is, like what proportion of people are children. And that exact proportion is a random variable subject to basically every time somebody is born, okay, the number of people under 18 goes up. Every time somebody dies, okay, then the total number of people that goes in the denominator changes, right? So the proportion of people under age 18 is a proportion calculated by the total number of people under age 18 divided by the total number of people in the US, okay? And both of those numbers change every couple of seconds because somebody is born and somebody dies, okay? And so if we were to do a frequentist approach, okay, a frequentist approach requires us to kind of imagine a kind of magical scenario where I could freeze time at this exact moment, okay, where no additional people are being born, nobody dies, and I would be able to kind of, quote, count every single person in the population and know that exact proportion, okay? That's what a frequentist approach would require because it's assuming that this unknown parameter is a fixed value. But I would say in real life, it's silly to think of something like the population as a fixed value. And so, we would say, the proportion of people that's under 18, that itself is a random variable. It's subject to kind of these random forces of people being born, people dying, and things like that, okay? And so we're going to treat our unknown parameters as random variables. And if we use a random variable for that unknown parameter, or I guess another way to think of it is that probability reflects kind of a subjective belief. It reflects kind of, what is the probability that the proportion is between this, or also, if we go back to kind of the bag and the box and the marbles in here, now we're no longer worried about the actual count. We're not going to try to freeze time at that moment and count everything up. We're going to just say, you know what, this is kind of reflects what I believe to be the proportion in here, okay? It's kind of like based on the knowledge and information I have, this is the probability that something's in there, okay? I wrote, perhaps we were never actually allowed to look inside the box with the marbles, okay? And the probability of drawing a blue marble can be thought of as our subjective belief of what proportion is inside the box, okay? So kind of the key difference here in Bayesian statistics is that because we're treating these parameters as random variables, the parameters have their own probability distributions, okay? And so questions and any kind of calculations that depend on that unknown parameter are suddenly going to get a lot more complicated because we no longer have a single value, but instead we have an entire distribution associated with that unknown value. So if we're thinking about kind of the box or the bag with marbles in there, we sampled 10 marbles and 6 of them were blue. The frequentist approach, we would say, okay, according to maximum likelihood estimation, my best estimate for the proportion that's blue is 60%, okay? And then we would create like a confidence interval that puts a margin of error around the estimate. But as far as doing future calculations, we're just going to plug in that number, 0.6. We just plug in that one number, assuming it's 0.6. And I said, part of me is a little uncomfortable about assuming that the proportion is this exact value. after just 10 observations. After just 10 observations, to assume that the exact value is 60%, it's a little uncomfortable to me, okay? So with a Bayesian approach, the proportion of blue marbles in the box will have a probability distribution, okay? And when we look at that probability distribution, the probability distribution will be the tallest at 0.6, indicating that that's the kind of the most likely value for the unknown parameter. But we'll also say, hey, you know what? If you've only observed 10 marbles, where 6 of them were blue, there's a decent chance that the proportion in here is like 55% blue, okay? Or 65% blue, or some other number that's not too far away from 60% blue, okay? There's even a small probability that the proportion in this bag is like 30% blue, okay? Because the proportion in the bag could be 30% blue, and just kind of by random chance, I happened to get a whole bunch of blue marbles, and I ended up with 60% blue. You know, I got 6 blue out of 10 marbles. So we want to kind of leave that as a possibility. And so this is kind of what our distribution kind of reflecting like what theta could be, okay? So theta, you know, what is the proportion that it's blue? It could be technically anywhere from 0 to 100% blue, okay? But we're going to say 60% blue is kind of the most probable. That's going to be right up here. But we're also going to say, hey, you know what? 50%, 55% blue. I don't think any of us would be shocked, right? If I drew 10 marbles and 6 of them were blue, and then later on we did actually dump out the bag and counted them up, and I said, oh, guess what? It was actually 50% blue. I don't think anybody would be shocked by that, right? It'd be like, oh yeah, that sounds reasonable, okay? And then on the other hand, if I said, oh, it's actually 70% blue, you'd say, okay, yeah, that also sounds reasonable, right? Because these are all kinds of things where we say, yeah, you know what? If that were the actual proportion that's in here, I could understand how we end up getting 6 blue and 10 marbles, okay? It would be a different story if we had 1,000 marbles and 600 were blue, okay? Then we would be surprised if it was actually only 50% blue, or if it's actually 70% blue. But 10 marbles, 6 blue, we'd say, yeah, any of these values between 0.5, 0.7, pretty likely, okay? And again, you know, even at 0.3, it's not super likely, but we're gonna say it's not impossible either. It's not impossible for the proportion in the bag to be 30% blue. So this is kind of a picture reflecting the distribution of theta after observing 6 blue and 10 marbles, okay? The trade-off now, though, okay, of taking this approach, you know what, let me give you your first view quiz answer. First view quiz answer is the letter C, C as in cat. C as in cat, okay. Trade-off is that our calculations are a lot more complicated, okay? So for example, if I said, hey, what is the probability that I get 2 blue marbles? I'm going to draw 3 more marbles from the bag, and what's the probability I get 2 blue marbles, okay? Frequentist answer, it was easy. We just plugged in 0.6 and we got our answer, okay? But now for the Bayesian answer, how do we do our calculation? I don't have a single value for theta. I'm saying like theta could be any of these things where some of these values of theta are more likely and other values of theta are less likely, right? So technically what we would have to do is we would have to do like a big kind of integral here, okay? We'd have to consider all of the possible values of theta, okay? That theta could be technically anywhere from 0 to 1, okay? And we also want to account and weight that by the probability that theta is that value. So we're going to say, 0.6 has a higher probability. We weight that heavily. 0.2 has a much lower probability. We weight that accordingly. Okay. All right.
Question.
Yes.
So you said that you increased the 10 to 1,000.
Yeah.
That would be more surprising. Isn't it like the same standard deviations away if it was 5 versus 500? The sample size.
Yeah. So okay. Well, let's just think through that, right? So if I draw 10 marbles, and 6 of them are blue, okay, and I say, hey, guess what proportion in here is blue. You'd say 60%. Okay, that'd be your maximal length. But then I say, okay, well let's open up the bag and dump everything out. Okay, and we did count everything up, and I say, oh, surprise, it was actually only 50% blue. Okay, you'd say, okay, right? You'd just go, okay, that's fine. Okay, all right. Let's say I get another bag, like a different. I got a bunch of marbles in here also, and then I said, we're going to sit here all day, and we're going to count marbles. And I draw 1,000 marbles out. Okay, 600 of them are blue. Okay, so what proportion do you think is blue in the bag? 600 out of 1,000. You'd say, okay, 60%. Okay. If I were to dump everything out, okay, and then it turns out it was 50% blue, I think that would be surprising that case. Okay, even though it's only a 10% difference, the fact that we had observed 1,000 marbles, okay, where 600 of them are blue, I think we would feel a lot more confident that it's got to be something close to 60% blue, right? If it was like 59% blue, 61% blue, I think that would be understandable. But to find out that is only 50% blue, I think that would be more surprising, right? Or is that...
So what changes about like this route? Like this thing, it was like...
Yeah, what changes is basically the width of this thing. It becomes a lot more narrow around 60%. Okay, so yeah, we're going to get into that regarding the beta distribution. Okay, so I'm going to use an example. This is adapted from another example, and so I don't know if anybody's into baseball. The regular season, well, actually, there's a doubleheader today. That's going to determine like who's going to be playing in the playoffs. But anyway, for most of the other teams, the other 28 teams, the regular season ended, and anyway, all kinds of in baseball, there's all kinds of statistics that are being tracked, how well the batters perform, and a very common one that's tracked is batting average. Okay. And the way you calculate batting average is the proportion. You do the number of hits divided by the number of at-bats. Okay? At-bat is basically, it's a little bit more complicated, but basically every time a batter steps up to the plate to try to hit a ball. Okay? It's a little bit more complicated. What I define as technically a plate appearance, but batting average is basically every opportunity the batter goes up to try to hit the ball. Okay, and in Major League Baseball, it is really hard to hit a ball. Okay, I don't know if you've ever been to a batting cage, but if you just like step into like the 70-mile-per-hour batting cage, it is like your first time. It's like scary seeing that ball come at you at like 70 miles per hour. And then in baseball, the pitches are frequently over 90, close to 100 miles per hour for fastballs, and then they have curveballs that suddenly change. It's really hard, and so and basically in order to kind of stay employed in Major League Baseball as a batter, there's an expectation that your batting average is going to be over 200. In baseball, these proportions are so kind of tight. We read off basically 3 places after the decimal, and this is batting 200, or basically 2 out of 10. Okay, 20%. You're expected to hit at least 20%. And if your batting average is below 20%, you are at risk of getting demoted. Okay, or basically waived or kicked off the team, or sent down to the minors. Okay, so this is kind of the expected minimum batting average. Okay, meanwhile, okay, a batting average of 300 is considered to be excellent. Okay, so the difference between a player that's about to get cut and dropped from the team and a very good batting average is just kind of this small window, right, between 0.2 and 0.3. This is kind of the difference between, not a very good player to, a good one. Okay, Shohei Ohtani almost clinched the Triple Crown, batting Triple Crown. So he finished the season. He had a phenomenal season, and his batting average was like 0.310. Okay, 310. Okay, so most players are going to have a batting average below 0.3 or 300. Okay, the highest career batting average of all time in all of history of baseball. Okay, is 0.366. That's the highest ever. Okay. And then a batting average of 0.33 or higher for a single season is considered to be really, 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 really good. Okay? So let's say a team hires, so this is kind of the background information you need to know about batting averages. Okay? Let's say a team hires a new player. Okay? So somebody, they've been coming up through the minors or whatever. We don't know what this player's batting average is going to be in the major leagues. Okay? So this player's batting average is unknown to us. Okay? Let's say this player, in their first 10 at-bats, okay, in the MLB, let's say this player gets 5 hits. And so therefore, his batting average so far after 10 at-bats is 500. He got 5 out of 10. He's gone 5 for 10. So his batting average is 500. If we were to take a frequentist approach, and I say, hey, what do you think is the probability that this player is going to get another hit at his next at-bat? Okay? The frequentist approach would say, hey, look at the data that we have so far, and let's do a maximum likelihood estimate. And we would say, well, so far he's batted 500, therefore, I think at his next at-bat, he's got a 50% probability of getting a hit. Okay? That would be the frequentist approach. Okay? However, for anybody who follows baseball, we would say that is way too optimistic. Okay? Our gut feeling tells us that by the end of the season, okay, this player is not going to be able to maintain this pace of batting 500. Okay, of batting, hitting 50% of getting a hit 50% of the time. So how do we incorporate kind of just our knowledge about baseball and just how, it's pretty unusual for somebody to bat over 300 into our calculations Okay, does that kind of make sense? That we don't want to just say, hey, let's just take our data, let it speak for itself. All right, he's got 10 at bats, he's got 5 hits. Okay, his proportion is 0.5. Okay, we don't want to just say that. We want to say, you know what? Let's take into account that, yeah, in baseball, these are the numbers. Okay, so we want to try to incorporate our knowledge about baseball into what we call the prior distribution. Right. So we want a distribution where almost all of the values are over 200, and most of our values are below 300. This is, in my opinion, I'm following this website's numbers. In my opinion, they're a little bit generous on what a batting average is. Okay, but basically, if here's our distribution going from 0 to 1, and we want to kind of draw like where we think batting averages should be around, okay? And so let me just, oops, didn't want that. Wait, how do I exit full, oh, here we go. Exit full screen. So if you go to Baseball Reference, this is kind of like team averages and things like that. You can see the entire team has a batting average. So the Diamondbacks have batting average of 0.255, at the Braves batting average of 0.260, Orioles 0.258, 0.267, 0.262, so on and so forth. So these are kinds of so you see a lot of kind of batting averages that are around 0.25 and 0.26, okay? And just kind of real small differences, 0.256, 0.262 to 0.250 to 0.265, okay? That's kind of like team averages. And then if you look at any one of these teams and whatnot, and you look at, where are their players? People, current batting, okay? So these are kind of the individual batting averages for the different, I guess they have like everybody listed here, but batting average of around 0.26 something here. Okay, it's hard for you guys to see, but anyway, we want to kind of incorporate that into this, okay? And so we might draw something like this, right? So where basically my entire distribution is basically between 0.2 and 0.34, 0.35, something around that, okay? So this kind of reflects like if we were to pick a random player in Major League Baseball and try to guess what their batting average is, it might look something like this, okay? And so to kind of do this, we would use the beta distribution, okay? So the beta distribution is a continuous distribution that's defined only on the interval 0 to 1, okay? And we frequently use the beta distribution to model a random proportion. So it's like a distribution of proportions or a distribution of probabilities, because proportions are always going to be between 0 and 1. So the beta distribution is going to be between 0 and 1. So it makes sense to be used for a proportion. Okay, the PDF of the beta distribution is 1 over beta function with parameters alpha and beta, or A and B, theta to the alpha minus 1 times 1 minus theta to the beta minus 1. Okay, this is the PDF. And then this constant, okay, the beta function of alpha comma beta is found by doing gamma alpha times gamma beta divided by gamma alpha plus beta, okay? And so this, unfortunately, this constant looks scary, right? Because we're not really used to the gamma function. We're not used to this kind of beta function. And so while this value for this thing feels scary, it's a constant, okay? It's just some number, and it's only there so that this portion over here, that when you take the integral, that the entire integral is 1, okay? Because all probability distributions, that's like its requirement, is that when you integrate across all of the possible values, the integral is equal to 1. So this thing over here, that's all its only purpose is to just kind of make sure that the actual part that we're interested in integrates to 1, okay? These shape parameters, alpha and beta, you can kind of think of them as how many yes and how many no values that we've observed in our data, okay? Let me give you your second view quiz answer. Second view quiz answer is C. C as in cat. C as in cat. So kind of how many yes and how many no values that you have, and so the resulting beta distribution will kind of reflect what is the probability of yes, right? So you'll generally have a peak around alpha, the number of yeses, divided by alpha plus beta, yes and no's, added together, total number of observations. And then the beta distribution will have more spread, okay, if alpha and beta are have a low sum, and will have less spread, kind of a narrower interval if the sum of alpha and beta is high. And so I just have a bunch of examples of what alpha and beta look like. So if you just have alpha 1 and beta 1, you actually just get the uniform distribution, okay? So basically, all values between 0 and 1 have equal probability. If you have alpha 2 and beta equal to 2, okay, then the most probable value is 0.5, but really we have kind of high probabilities anywhere between all over the place here, okay? As we increase the alpha and beta, okay, so here I have alpha and 5 and beta equal to 5. I'm going to keep these equal to each other. It's going to stay centered at 0.5, okay, but the distribution gets more and more narrow, okay? So again, it's kind of like if we drew marbles out of this bag, and let's say we saw five red and 5 blue, okay? And I'm asking, hey, what's the proportion of blue marbles in the bag? Or I guess, what's the proportion of red marbles in the bag, okay? 5 red and 5 blue. Well, you know, your best guess right now is around 0.5, but, you know, other proportions are also have high values, okay? But as we increase alpha and beta, so now alpha is 20 and beta is 20. This is like saying, okay, out of the bag I've drawn 20 red and 20 blue. What's the proportion of red in the bag, okay? Now we're feeling a lot better about it being 50% red, okay? And we're pretty confident that it's not going to be 80% or 90% red, okay? Here it is at alpha 50, beta equal to 50, and you can see it just kind of getting more and more narrow, okay? Let's say you have, what if alpha is equal to 1 and beta is equal to 99, okay? With alpha equal to 1 and beta equal to 99, now, so we're saying we drew out of this bag 100 marbles, 1 was red, 99 were blue. What is the proportion of red marbles in the bag, okay? Our guess for what proportion is red in the bag is going to be very, very low, okay? Something close to 0 or 1%, okay? So we have this very kind of a peak over here and very kind of right skewed, okay? Here I have alpha equal to 2 and beta equal to 98. So if I drew 100 marbles out of the bag and 2 of them are red and 98 are blue, this reflects my distribution there, okay? With alpha equal to 5 red and 95 blue, what's proportion is red, okay? Now it's something closer to 0.5, okay? And as I change kind of the relative rates of what my alpha and beta are, we could see it being reflected in the distribution. So here's alpha equal to 10 and beta equal to 90. You got 10 red and 90 blue. What proportion of red do you think it is? Something around 10%. It might be a little bit higher, might be a little bit lower, okay? Here's alpha 20, beta 80, alpha 30, beta 70, alpha 40, beta 60, and so on and so forth. Alpha 70, beta 30. Okay, so this is what we have. Does that kind of make sense as far as the shape of our distribution here? Here, if I change, I'm going to keep the ratio between alpha and beta the same. So alpha is going to be basically 7 to 3, okay? Beta is going to be 30, alpha is 70. We're going to keep that ratio of 7 to 3 the same. So here I'm going to slightly reduce it to 63 and 27, okay? Notice what happens to our distribution. It gets a little bit wider, right? So going from 70 and 30 to 63, 27, basically we're still, our peak is still around 70%, but we're not as, I guess not as confident. We're gonna say our values could vary a little bit more, okay? 56, 24, 49, 21, 35, 15, 21 and 9, 7 and 3. So as I decrease the sum of alpha and beta, we could see our distribution getting kind of wider and wider, okay? Indicating that at this point, right, let's say I've drawn 30 marbles out of the bag and and we get 21 red and 9 blue, okay? Our best guess is still around 70%, but because I've only observed a total of 30 observations, if somebody came along and said, you know what, the actual proportion in the bag is 60% red, okay? We would say, okay, that's believable, okay? But over here, if I've observed 100 marbles, 70 of them are red and 30 are blue, okay? Now, the probability that something is actually only 60%, you know, that we have a lower probability of that there, okay? So that's reflected by the shape of our distribution here, okay? This is going kind of in the opposite direction, 70 and 30. If I continue to increase, right? So we're going to keep that ratio of 7 to 3, but here I'm increasing to 140 and 60, 350 and 150, 700 and 300, right? So this is saying I've observed 1,000 marbles out of the bag, 700 of them are red, 300 are blue, okay? So my peak is at 700, or 0.7. And now I'm very confident, okay? So this is what the distribution looks like if if you've observed 1,000 observations. Now we're very confident that it's something around 0.7, and that if somebody were to say, you know what, the proportion in the bag is actually only 60%, okay? We would say, yeah, there's no way that could be the case, because if it was actually only 60%, how could you explain that I drew 1,000 marbles where 70% of them are red? Okay, so the difference between 60% and 70% is a big deal when you have 1,000 observations. Okay, when you only have 10 observations, the difference between 60% and 70%, it's not a big deal at all, right? It seems very kind of reasonable or easy to explain that away. But with 1,000 observations, okay, now you have like a mountain of evidence, okay, that the proportion is something very close to 70%. So that's what we have here. Okay, so the beta distribution is used to kind of explain how, or is a distribution that shows us like what proportion we think something is inside, you know, some unknown bag or some unknown proportion that's something that's unknown to us. Always something between 0 and 1, and we kind of use our shape parameters alpha and beta to kind of reflect, you know, where we believe it to be centered. The kind of the ratio between alpha and beta is going to be where that distribution is centered, and the sum of alpha and beta is going to kind of change how wide or narrow that distribution is going to be, right? So this is, if you observed 10 observations where 7 are red and 3 are blue, this is kind of what you get, versus when you have 700 and 300, it looks like this. So this is, we're going to leave off here, and we'll continue up on Wednesday. But going back to the baseball example, we've picked these shape parameters using alpha equal to 81 and beta equal to 219, and that's going to produce this distribution here, okay? And this is going to produce a distribution where most of our values, almost all of our values are above 0.2. The vast majority are below 0.3, and we have, you know, basically no one over 0.4. And that kind of aligns with, you know, our overall experience of batting averages. Maybe a little bit generous on batting averages, but kind of aligns with what we think, you know, Major League Baseball's batting average should be. Okay, I'm going to end the recording here.